Here are our objectives for today. 3.4. Number 1, use a rational zero theorem to find possible rational zeros. I call it rational root theorem because that's what they call it in the Algebra 2 textbook, if you remember that at all. Number 2, find zeros of a polynomial function. Number 3, solve polynomial equations. Number 4, use the linear factorization theorem to find polynomials with given zeros. And then number 5, use Descartes' rule of signs. Okay? Now, you guys have heard of this guy before, whether or not you realize it. Descartes did a whole lot of geometry stuff, and that's why it's called the Cartesian plane after him, after Descartes. Okay, just so you know. Okay, so first of all, use the rational zero theorem. Well, the rational zero theorem says if I have a function or a polynomial like this, f of x equals negative x to the fourth plus 3x squared plus 4. The way we can find the possible zeros here are by taking, here let's see, possible zeros are going to be, it's going to be all of the factors of the constant divided by all of the factors of the leading coefficient. Okay, so all the factors of the constant divided by the factors of the leading coefficient. So in this particular problem, where is the constant? Or what is the constant? It's 4, right? What are all the factors of 4? 1, 2, and 4, right? Whether this is a negative 4 or a positive 4, there's still some things we have to take into account. Okay? It's a negative 4, so isn't it 1 times negative 4? Or negative 1 times positive 4? Or negative 2 times positive 2? So we have to take into account the positive and the negative of each one of these numbers. But even if it was positive 4, wouldn't I have to take into account negative 4 times negative 1? And negative 2 times negative 2? Right? We still have to take into account the positives and the negatives of each number. And we have to divide that by the factors of the leading coefficient. Well, in this particular problem, leading coefficient is just 1. Well, negative 1, but still. Okay? So I have to divide it by a plus or minus 1. Anytime I divide anything by 1, I just get what I was dividing in the first place, right? Okay, so the cool thing about this is the zeros of this function right here are going to be in this list right here unless they are not real. Okay, which we're not dealing with right now, just for the record. Okay, so we have a couple choices. Okay, there's only 6 possibilities right here. How many answers should I get? At most, I should get 4, right? At most, I should get 4 because that's my degree. But I could have multiplicity, right? I could have numbers that repeat as factors, things like that. But I only have 6 possibilities, so I could choose to do all of these with synthetic division. If I do them with synthetic division, what am I looking for? A 0 as a remainder, right? 4, 3, 2, 1, 0. Okay, so I put all my placeholders in. Negative 1, negative 1, negative 1, negative 1, 2, 2, 2, 2. That's not going to be 0, is it? So 1 is not going to be one of my factors. What about negative 1? Negative 1, 0, 3, 0, negative 4, negative 1, 1, 1, negative 1, 2, negative 2, negative 2, 2. Still not going to be 0. 2, negative 1, 0, 3, 0, negative 4. Negative 1, negative 2, negative 2, negative 4, negative 1, negative 2, negative 2, negative 4. 0. That's not 0. Did I miss something? I did. What did I miss? Negative 2, negative 2, negative 2, negative 4, negative 1. That's a negative 2. Add that. That's supposed to work. Can you guys see what I missed? Yeah, they're both, negative 2 and positive 2 are both supposed to work. Negative 1 multiply negative 2, add negative 2, multiply negative 4, add negative 1. Multiply negative 2, add negative 2, multiply negative 4. Yeah, I don't know. It's supposed to work. I'll do it again in a minute and see if I can figure it out. Unless I'm looking at the wrong example. I apologize. I'm looking at the wrong example. Please forgive me. Negative 2. Negative 1, 0, 3, 0, negative 4. Negative 1, 2, 2. Negative 4, negative 1, 2, 2, negative 4. So these are the last two possibilities, 4 and negative 4, if there's going to be an answer that's real at all, right? Negative 1, negative 4, negative 4. Well, that's not going to work. Can you tell ahead of time that's not going to work? Because this is about to be negative 16, and this is just going to get bigger and bigger. Okay, negative 4, negative 1, 0, 3, 0, negative 4, negative 1, 4, 4. See, that's not going to work either. So in this particular problem, if all it asks you to do is find the possible zeros, that's this right here. If it asks you to find the zeros, we looked the way that we knew how, right? One of the ways that we knew how. The other way that we know how to look is by looking at our calculator. Okay? Making a new document, that is a graph. We enter negative x raised to the 4th plus 3x squared minus 4. Now, can you see why that might have been a better idea to start with? What do you notice? It doesn't cross the x-axis. If it doesn't cross the x-axis, there's no zeros. If it says you have to solve using the synthetic division, well, okay, we did that. It didn't help us, though, because it didn't give us any zeros. Whereas if we would have looked at our graph first, we would have noticed there's not going to be any zeros because it doesn't cross the x-axis. No, not negative leading coefficient. Remember, it's going to be opening down since that was an even. Since that was an even exponent, they're both going to open the same direction, the left and right behavior. But it goes down. So since we knew that the interception, the y-intercept was negative 4, we could have known beforehand. But yes, yeah. So although I just didn't know how high these were going to go. Does that make sense? I know it's crossing the y-axis at negative 4 because that's my y-axis right there, my y-intercept. But I didn't know how high these were going to go to know if it was going to touch the axis or not. But yeah, that's a good way to think about it too. Probably some people can. I cannot. Yeah. Okay, so do you understand at least this first part of it right here? I know this didn't help to show you a lot, except it helped us practice synthetic division and it helped us know what we were looking for if we're doing synthetic division, right? We got to have a 0, and look, I even wrote a 0 there and it's not even a 0. Ignore that part. Okay? If I ask for the possible zeros, though, of a function, can you tell me the possible zeros? The only time that it gets difficult, quote-unquote difficult, is when the leading coefficient's not 1. If this happened to say negative 3x squared, like that, we would have to divide by plus or minus 1 and plus or minus 3. Well, if I divide everything in the numerator by 3, I'd also have plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. So still the benefit of knowing this is if I just gave you that equation without anything and said find all the zeros and do it by synthetic division, we have an infinite amount of numbers to try for synthetic division. Okay? This pares it down to just 12. And while that seems like a lot, 12 is actually a lot smaller than infinity. A little bit. Okay? It takes a lot less time to just divide 12 than it does infinity. All right? So are you feeling good about the rational zero theorem? That's what this one is. Possible zeros is the factors of the constant divided by the factors of the leading coefficient. You okay with that? Okay, so finding of zeros of polynomial functions, we actually just talked about that. We can either do synthetic division or we can look at the graph. Now, why is looking at the graph not always going to work? When it doesn't cross on an exact x. That's exactly right. Okay, let me change this to +4 real quick and watch this. So there's 2 right there, right? So, oh, that's really nice because it does cross at -2 and +2. That's the example I was looking at in the book a minute ago that I was trying to say that -2 and +2 work, right? Well, this is really easy to tell, right? But what if it said this? 5. Does that cross at +2 and -2? Kind of looks like it, but if I go to Control T, +2 and -2 are not 0. See what I'm saying? Okay, so that's not cool because then I would have to know what these what the possible zeros were, and I'd either have to, number 1, do synthetic division on all of them to figure out which one it was, or can I show you another way in the calculator to do it? Okay. If I go to either my scratch pad or to a document that's a calculator, here's what I can do. I'm going to say, let's start, what did I change this to? 5 plus 5. So I'm going to, let's just pick, first of all, it would change this whole list. You understand that, right? It would change the whole list. So I'm just going to keep using that equation and just kind of talk you through how you would do this. Okay, first of all, I'm going to say that 1, we're going to store 1, store using control and vars right here, store it as x. Okay, and it tells me, okay, 1, that's fine. Now I'm going to say to my calculator, -3x squared, no, raised to the 4th, oh, stop it, jerk calculator, raised to the 4th, and then plus 3x squared minus, or was it +4? No, it's -4. Like that. Well, what does that say? -4. That means the calculator took a 1 and plugged it in everywhere there was an x and evaluated it. How do I know if it's a 0? If that's 0, then I know it's a 0. Okay, that's another thing that's kind of cool. If you evaluate the function at that value and it's 0, it is also a 0 of the function. Okay, so there's 2 ways you can use your calculator to figure this out. This is really nice when you want to try 1/3 as x. Because I don't want to put 1/3 in there because then I'm just going to go get the equation I just used and press enter again. If that's not 0, I don't care what it is. I care that it's 0 or not. Okay, so that's another way to figure out where your zeros are to find the zeros of the polynomial function. Okay, if we're solving polynomial equations, excuse me, if we are solving polynomial equations, let me get to the example that I want real quick. Well, where did it go? There it is. X raised to the 4th minus 6x squared minus 8x plus 24. Now you're going to know it wants you to solve it because it's going to equal something. Okay? Whatever it equals, we want it to equal 0 so we can do all this stuff to it. Okay? So let's see if we can solve this by finding all the zeros first. Okay? Because if we know the zeros, then we know the factors. We haven't talked about that in a couple weeks or so, but let's make sure we understand how to do it. Okay? So all the possible factors are all the factors of the constant divided by the factors of the leading coefficient. So 1, 2, 3, 4, 6, 8, 12, and 24, all divided by the factors of the leading coefficient, which is 1, which means everything that I divided in the top divided by 1 is just everything in the top, right? Everything in the numerator. So these are the only things I have to look for, right? Now I'm not going to do that though, because I'm smarter than that. Except I can't figure out how to work the calculator. So I'm going to go to my current. I want to get rid of my table. So Control T. And I want to tab and I want to change this equation. So I'm going to clear it and enter my new equation here. X raised to the 4th minus 6x squared minus 8x plus 24. And I'm going to look for zeros on this calculator right here. Well, if I have to look and check, I have to make sure all of these, it might be a little easier to look at the table. I know for sure I've got one at 2, right? Positive 2. But how many should I get? I should have 4, right? I should have 4 factors. Again, some of those might be multiplicities and things like that, but I ought to get 4. So I have a couple choices here. I can go look at the table, which is what I think I'm going to do. And then we'll go from there, okay? So Control T. I'm going to go all the way to negative 24. Okay, negative 24 is not 0. Negative 12, not 0. Negative 8, not 0. Negative 6, not 0. Negative 4, negative 3, negative 2, negative 1. Okay, so none of those are zeros. 2 is a 0. I've got that one already. I need 3, I need 4, I need 6, I need 8, I need 12, and I need 24. Okay, well none of those are zeros, so I know for sure that I have a 2. That's all I know for sure, right? So at this point, it would probably be a good idea to do synthetic division to see what's left and see what I can do from there. Okay, so if I do synthetic division with my 2, I have a 1, a 0, a negative 6, a negative 8, and a 24. 4, 4, 3, 2, 1, constant. So 1, 2. 2 multiply 4, add negative 2, multiply negative 4, add negative 12, multiply negative 24, add is a 0. Right, I knew that was going to be a 0 because it told me that I was going to be a 0. I saw both in the table and on the graph that on the table the y was 0 when the x was 2, and I saw it on the graph that that's where it crosses, right? Okay, or touches in this case. So what I have left is x cubed plus 2x squared minus 2x minus 12. Now, I'm gonna use always, although I don't like to use that word. You guys know that, okay? But how about most of the time? Okay, most of the time when the graph comes down and touches this part right here, it means because that's a multiplicity. You see how it just touches and goes back up? That's a multiplicity. So I know that if I took this, it's going to be messy, okay? And I did a 2 again, I should still get a 0 as my remainder, okay? So I'm going to do that. 1, 2, 4, 8, 6, 12, 0. Okay? So this is x squared plus 4x plus 6. Now, what multiplies to be 6 and adds to be 4? Nothing, right? That's why we didn't see it to begin with. Otherwise, we would have been able to see it to begin with. All right? So, do you know how to solve a quadratic? How? We could look at the graph, okay? But we know from looking at this graph, we're not going to be able to see anything, okay? And so, probably we need to solve this with the quadratic formula because it's not going to be a real answer, right? It's going to be imaginary. It's going to have an I in it. So if we solve this with the quadratic formula, we'd have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We sing that a lot in Algebra 2, remember? So x equals negative 4 plus or minus the square root of 16 minus 24. So do you see why we didn't see it before? What is 16 minus 24? Negative 8. What is, except I forgot my square root. What is the square root of negative 8? Well, I don't know the square root of negative 8, but I know the square root of negative 1. The square root of negative 1 is I, right? I also know that 8 is 4 times 2, and I know the square root of 4 is 2, and I don't know the rest of the square root of 2. It just has to stay there. Now I know that all three of these terms are divisible by 2, so I can simplify that to give me x equals negative 2 plus or minus I root 2. I know, it's been a while since we've done that, isn't it? Okay? But it's still something we've got to be able to know how to do. Okay? So, do I have my 4 answers? I've got this one, and I've got these two, right? So what we need to be able to do is know that those are the zeros or the roots or solutions. Okay? 2, 2, negative 2 plus or minus I root 2. Those are my 4 solutions. Then if it asks for the factors of that, you have to remember to do that. How are you going to remember to do that? Yeah, that's the number that goes on the outside of the synthetic division. So the factor it came from is opposite sign of that. Or if it's x equals 2, we have to subtract 2 from both sides to get the factor. Remember that? And then these, what do you think the factors look like for those two? For these two? Whack. X plus 2 plus I root 2 and x plus 2 minus I root 2. Okay, because it's minus that. Does that make sense? So, solving polynomial equations. I chose one that was particularly hard to begin with because that was a lot of steps. They're not all that hard. Sometimes you're going to be able to solve it by looking at the graph and seeing all 4 places that it crosses the graph. Or you're going to notice that it comes down and touches the graph and goes off, so you know that's going to be a multiplicity, right? So you know that that takes care of 2 of them right there. All right? Using the linear factorization theorem. Let's talk about that real quick. Before we talk about that, I need to remind you of the fundamental theorem of algebra. Do you remember the fundamental theorem of algebra? We've already talked about it twice this period. If the degree is 4, what's the maximum number of solutions that I should get? 4. That's the fundamental theorem of algebra. It actually says, technically, if f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. Okay? So, linear factorization theorem. Okay? We kind of already did it on this example, all right? Because we found all the zeros and the roots right here, and we said these right here were the factors. Well, if we know the zeros, we can write the factors, and because we have the factors, this is the linear factorization theorem. If I'm given this problem, I can factor it by writing it as a product of factors. Okay? Linear factorization theorem looks like this right here. Okay? Blah, 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 blah. If this is true, then you can write it like this. You can write it as a list of factors, which is what we just did on the last example. Okay? So they're complex numbers, real and not necessarily distinct, which means like the x minus 2 and x minus 2 like we had a minute ago. Things like that, where each factor has a leading coefficient of 1. So if there was something else, then we've already factored it out. Okay? So we actually did linear factorization theorem without me telling you it was a linear factorization theorem. All right? If we're given a problem, we can write it as a list of factors. And then the last one is Descartes' rule of signs. Okay? F of x equals 3x to the 7th minus 2x to the 5th minus x to the 4th plus 7x squared plus x minus 3. Example. Here's my example. Okay? What sign is the first number? Positive or negative? Positive. So it goes from positive to negative. Do you see that that's a sign change? Now, from here to here, is there a sign change? No. From here to here, is there a sign change? That's another sign change. From here to here, is there a sign change? From here to here, is there a sign change? That's a sign change. Okay? So, the number of I'm going to have to write this down for you. The number of, first of all, the number of positive real zeros of f is either the same number of sign changes so in this case 3 or less than the number of sign changes by a positive even integer. So let me make sure you understand that. The number of positive real zeros, positive and real, in this case is either 3 or what? By a positive even integer. So in this case, either 3 or 1. So like 2 less, basically. So if this was a 7, if this was 7 sign changes, it would be 7 or 5 or 3 or 1. Does that make sense? If it was a 12, it's either 12 or 10 or 8 or 6 or 4 or 2. By a positive even integer. So it's like 2 less, basically. It could be 10 and 2, because that would still be less by a positive even integer, less than 8, right? 8 less. Yeah. Right, but if you start with 7, you count down by a positive even integer. Yeah. Okay? Okay, so those were positive real integers. The other possibility is that there are negative real, that was positive real zeros. The other possibility is that you can find the number of negative real zeros of f. It's, oh goodness, it's either the same number of sign changes, but this is different. It's f of negative x, and we'll talk about that in just a second. Okay, this one was just of the function f of x. This is f of negative x, or, I guess I should have put or up here, or less than the number of sign changes of f of negative x by a positive even integer. And then there's a little stipulation thing down here. It says if f of negative x has only one variation in sign, or one change in sign, then f has exactly one negative real zero. So if we look back at this problem up here, let's talk about f negative x. Okay, that means I'm going to take this whole problem right here, and instead of having an f, I'm going to put an, instead of having an x, I'm going to put a negative x. And I'm going to see if that changes the sign on the problem. Okay, if I put a negative x right here, negative x to the 7th, does that keep the 3 positive, or is it going to be a negative 3? It's going to be a negative. Okay, that's going to end up being negative 3x to the 7th. What if I put a negative in here with an exponent of 5? That's going to be positive 2x to the 5th, isn't it? Now what if I put a negative x here? If I raise it to the 4th power, is that going to still be the same thing that it was before? Yeah, so negative x to the 4th. If I make this a negative x, is that going to be different or the same? It's going to be the same as it was before. If I put a negative x here, it's going to change, and then minus 3. Now we have to count the sign changes of f of negative x. So that's a sign change, right? That's a sign change. That's a sign change. That's a sign change. And then there's not one there because they're both negative, right? So here the number of sign changes is 4. Okay? So it's either 4 or less than that by 2. No, it just happened to in this case. What did happen though? If it's an odd integer, is it going to change the sign? Is it, if it's an not integer, if it's exponent, if it's an even exponent, is it going to change the sign? It's not. It's going to say the same sign as it was before. So that's like a little hint that you can go with. Okay? We'll talk a little bit more about this tomorrow if we need to. Otherwise,